It will not work. It will not work. Okay, so we're going to be starting our first algorithm, which is the linear regression algorithm. This is the first machine learning algorithm we are starting. So we're going to be answering a few questions. One, what kind of problems can we solve with such an algorithm? Right? Again, the thing we are supposed to focus on is how this algorithm functions, the mechanism behind the functioning of this algorithm, right? That's what we're going to be laying emphasis on today. So let's start by answering the question that what kind of problem does the algorithm solve? First, it's a supervised. If you went through the notes, you know what a supervised learning machine learning algorithm is. It's supervised, meaning that we have to label our target, right? So we have to label the targets. We have to label our targets, like you say, cancer, no cancer, right? Like we agreed. Okay. After that, now, the next thing we want to look at is what kind of problems it solves. It solves regression problems. It's used to solve what we call a regression problem. Now, what is a regression problem? Let's look at what a regression problem is. So for us to look at a regression problem, I'm going to have an example. Let's say you have somebody's marks, the marks you score in school, your GPA, and then your salary, right? Salary is your target. Let's say your marks in school, they want to use your marks plus your GPA to determine your salary, right? And so since you say it's a labeled algorithm, so we can have a marks like you scored, say 70 or 150, maybe 80, and then your GPA is maybe 3.0, 2.8, and then maybe 3.5. And then your salary is going to be like, let's say, 20,000. And then this one is going to be like 18,000 or something. And then let's say 30,000. So now a regression problem is a problem where you're actually solving the relationship between two numerical variables. Now, in this case, there are two options. The simple linear regression, which we are starting with today. Today, we are focusing on simple linear regression. Simple, and then there's multiple linear regression. And again, in simple linear regression, we are looking at one variable being a determinant to one target, right? Maybe, for example, we're using just your GPA in school to determine your salary. In the case of multiple linear regression, we'll be using marks plus GPA plus some other things, maybe your age and all of that. So again, the variables in this case must always be what? Numeric. So it must be numeric. So you cannot use it for categorical data. So your data must be numeric. That's the first. Those are some of the first thing we need to take into consideration. It must be numeric. And again, you can't go with categorical data or strings or whatever. Even if you have to do encoding, it doesn't still, that's not the kind of problems it solves. So again, you have to look at the situation whereby the variables you're dealing with are numeric. For example, GPA is a numeric variable, salary is numeric, so it has to be like that, right? So these are the kind of problems you solve. And so you are trying to see how you can predict salary using somebody's GPA. So in this case, let's focus on simple regression, simple linear regression. And so I'm going to take out the column for marks. Let's only stick on GPA, right? So now, in that case, we're going to be predicting your salary based on your GPA. The GPA is your score in school and something like that. So now, how does the algorithm do this prediction? How does it do this prediction? You start by training your algorithm. We talked about this extensively in our last class, right? So you start by training your algorithm. And how do you train your algorithm? You take your data. Let's assume we had a data set that talks about GPA and salary. We take this data, we give this data to that machine learning algorithm. You remember the case where I was talking about uh, looking at my neighbor and then registering the umbrella and no umbrella scenario. And then I take that data, I give it to my machine learns from that data. And then when I come and put umbrella, I get rain, right? So that's the same scenario here. You take your GPA plus your salary data and you give it to the machine learning algorithm. It learns from that data. Then from there, now it can be able to make predictions as to the outcome of salary based on an inputted GPA. So after learning, if you then come and say somebody's GPA was say 2.7, it can now predict the salary of that person because it was able to learn from the data, right? And so again, we are dealing with all numeric variables. So how does it do that? So let's look at something. Please, if you are not muted, you have to mute yourself, please. Check, and make sure you're muted. Okay, let's look at something. I want to plot a graph of GPA against salary. So GPA, and then so let's say the GPA is set to let's start from 0, and then we have 1, 2, 3, 4, and 5. So we have here we're going to be having our GPA on the x-axis, and on the y-axis we're going to be having our salary, right? Salary, and let's say we have 10 in thousands. So if I write 10, you just write in thousands. And say 20, say 30, and say 40,000. So let's assume that we have our data points plotted like this. We have our data points plotted like this. Okay. So how this algorithm predicts is able to make predictions when you now give it a test data is that during learning, when you give it a data, when you're training the algorithm, during learning, what it does is that it creates what we call a line of best fit. Now, let me explain this detail because this is the brain behind linear regression. So what a line of best fit does is that it puts a line across, it plots the data points during training. After plotting the data points, it finds a line of best fit across the data points, right? A line of best fit. For some reason, I don't know how to draw a straight line. For some reason, let me try again. Nobody should just look at me and say, Prof, I cannot draw a straight line. I can draw a straight line. Okay, assuming that this is my straight line, this is my line of best fit. So if this is my line of best fit after plotting the point, that means when you now come and give me a GPA of 2.7 and after that what is going to be the salary, what the algorithm is going to do is that it's going to take 2.7 around here, 2.7 around here, and then it's going to come up to the line of best fit and then comes and get the corresponding GPA, which is maybe say your corresponding salary, maybe let's say 31,000 or so, right? That's how it's going to be the prediction. But then the question is, how does it draw this line of best fit? Because the reason is we can have a line like this, we can have a line like this, we can have a line like this, right? So how does it determine which line is the line of best fit? That's where the trick lies. So let's see. So what happens is that let's assume that. So for some reason, let me just delete some of these lines, all these lines. And then let me just clear the drawings and then let's do another drawing. So I'm going to do another drawing. Again, we have GPA down here. And then up here we have salary, right? Salary. So we have our different points plotted along the curve like this. As you can see, okay. So we get our first line of best fit. So now what it does is that it draws different lines and calculate the what we call the error or the residual. Let me explain. Let's assume that this is the first line that it draws, line 1. So this is L1, this is line 1. What is the residual? The residual will be the difference between the actual values which it has plotted to the line of best fit. So the difference between the line of best fit and the actual values is going to give us the residual. See, this difference like this is going to give us what we call the residual or the error, right? The error. So the difference between the actual point, let me explain what this residual means. Because the thing is that when you plot this point, you actually plotted real data. For example, on our table we had GPA here, and then we have salary here, right? So GPA was 2, 3, and 4. Salary was 20,000, 30,000, and 40,000. Now, if you notice, after drawing the line of best fit, what happens is that this is GPA 2, 3, 4, 5, for example. After drawing the line of best fit, if you come and calculate the value of the GPA of 2, if you come and take 2 and extrapolate it to the line of best fit and take it back to the salary, you'll notice that the salary will not be exactly 20,000. The salary might be, say, 10,000, then maybe 20,000 here, and then 30,000 here. The salary might say 18,000. So the difference between the real value and the predicted value is what we call the residual. So the residual here is going to be 2, right? Because it's going to now be using the line of best fit to do predictions in the future. So when it finally gets the line of best fit, it takes the values from the x-axis, matches the line of best fit, and then reads the corresponding value on the y-axis. And the difference between the actual and the predicted is what we call the error, residual. Now, it finds the line of best fit. The line of best fit will be the line where the residual is least. The sum of residual is this. So what am I saying? It's going to take the difference between this point and this point. It's going to put the value, say the value is 2. The difference between this point and the line of best fit, the value is 0.5. This one will be around 3. This one will be around 2.5. And then it's going to calculate all these residuals and then sum them up. And then the line that, so then therefore means if you draw another line like this and then do the same thing and count and do the sum of residual, draw another line like this, count it and do the sum of residual, draw another line like this. So if you notice the difference between this point and this line, this point and this line is bigger than the difference between this point and this line, this point and this line. So it's going to do this for all the points and then sum the error or the residual. And the line that gives the least sum of residual is the line that will be considered as the line of best fit. The line that gives the smallest residual is the line of best fit. Let me hold on there and ask if somebody has any confusion. Or let me just get some reactions before I continue.
So far, it's okay for me.
Great. Does anyone have any level of confusion about the error? Do you now understand what the error is? Because it's important. Going forward, we're going to be talking a lot about error, which is the residual. Okay, no error. So let's take ourselves back to some secondary school mathematics where we were talking about the straight line, right? If you do not do mathematics, don't be moved. In form 1, form 2, we did something. They say a straight line. The equation of a straight line is y equals mx plus c, or say plus b. Y is the gradient. M is the gradient. Sorry. B is what we call the y-intercept. Y-intercept. And y will be the y-axis value, right? Now let me draw a line. Let me draw a curve. and then explain what all of this was. So if I draw a curve like this, say a curve of salary against GPA, if this is that curve, right, this point where this line cuts the y-axis is called the y-intercept. So this is the point B. So if I have my equation of straight line y equals to mx, now which are the right two? Let me correct this thing. If I have my line of y, say y equals to mx plus b, this point, this b is this point where it cuts the y-intercept. And then this m is the gradient, and this is how we calculate the gradient, change in y-axis over the change in x-axis. So this is how you calculate the gradient. You take this one, the value here minus the value here. So let's assume that this is 30,000 and then this is 20,000. The difference is going to be 10,000, right? So take 30,000 minus 10,000, going to be 20,000, going to be 10,000, right? And then divided by the change in x-axis over the change in y-axis. So this is x-axis. So let's assume that the GPA here is 2 and the GPA here is 4. So 4 minus 2 will be what? 2. So it's 10,000 divided by 2. So we are saying that the gradient m will be what? 10,000 minus 2, 5,000. 5,000. That will be the gradient. That's how you calculate the gradient normally. Or that's the normal thing we used to know in secondary school kind of mathematics. Now, let's do something. Let's do something. I'm going to have this equation of straight lines still left up there, and then I'm going to say something. So this is my data. If this is my data and here is my GPA and here is my salary, and then let's say GPA is 2, 3 and 4, and you have 20,000, 30,000, and 40,000. Now, tomorrow. Now, x in this case, this x is the values for the GPA. So it will be the value for the corresponding value. So you remember when you want to plot a point, if I want to plot a point, say for if a value, let's say if I want to plot, so let me say I take a value of 3 and say 30,000, right? If I want to plot this point, this is the x value and this is the y value. We already know this when you were doing Cartesian planes and all of that. So this is x and this is y. And so your x value will be this, and then your y value will be the corresponding salary. So if you come and then you take this, you have what to do? How many minutes? How many minutes do you have? How many minutes? Just give me like 10 minutes or so. Thank you. So if I take these points, let's say 330, so I'm gonna have 30 equals to m times 3, right? Plus, now I don't know b because I don't know where that line is gonna cause the m, so I'm gonna put b. So I just wanted to know that x is 3 and then 30 will be your 30,000, sorry, is gonna be your y value. Now, how do you, so error, which is what we were calling the residual, will be, I told you, is the actual value minus the predicted value. So if my y is 30, so I'm going to have y minus y bar. So y here is the original value, like 30,000, and then y bar will be the predicted value, which was, we said it was 18,000 that time against 20,000, right? Which we took the difference and it was something, 30,000 minus 20,000. So if we took the difference and it was 10,000. So y bar will be the predicted value, while y, so my error function is equals to y minus y bar. So the original prediction, remember your target is the salary. You are using GPA to predict salary. So you are going to take the original salary value minus the predicted salary value to get the error. So when you get the error, so what we want to do is that we said you take the sum of error. Summation error is equals to the sum of y minus y bar. We know this already because if you are summing your error, that means you're summing y minus y bar. And we say the line of best fit is the line where the error, the sum of error is least. So it's the line where y minus y bar gives you the smallest value. So if you draw plenty lines across the data point, the line where the sum of the errors is going to be the least is going to be the line of best fit. That means if you take the difference between the original and the predicted and it's the smallest, that's going to be the line of best fit, because we want, under normal circumstances, we would have found the situation would have been that the original minus the predicted should have been 0, because if you predict exactly what is supposed to be, then it's going to be 0, but you never find an algorithm that works like that. That means when you do the performance of that algorithm, it's going to be 100%. It's always not impossible. It's not always possible. So you always get something like 98, 97, 95. So, but that means that there's an error margin there, right? So that's what we call the error. So now, how do you get the value of B and M? So if we are saying that y equals to mx plus b, that means we can also say, so we are saying that sum of error is equals to the sum of y minus y bar. And we are saying that y is equals to mx plus b. So, or y bar, sorry, is equals to mx plus b. And then we are going to say that sum of error is equals to the sum of y minus mx plus b, right? Mx bar plus b, mx bar plus b bar, something like that. So now this is going to be, so we are just replacing. So you now notice that the equation of error is now expressed in terms of m and b, because in that case, you know your y value, which is going to be 30,000. Your x value is going to be 3, but you don't know b and you don't know m. So how does it get b and m to be able to get the line of best fit? Because remember, the line of best fit has a y-intercept and a gradient. So for you to draw a line, you need to know the gradient and the y-intercept. So how does it get that? That's what I want to show you, and that's where we're going to be ending for today. So if I plot a graph of y or error, so let me plot it this way. If I plot a graph of the error against let me see if I have. So let me just pull up something here, okay? Okay. Let me open a blank slide. So if I plot a graph of error against, so if I have my equation of, so let me clear these drawings and then I have something here. So my equation of error now becomes equals to summation from x equals to I to n of y minus mxi plus b, right? Which is what we call our, I think it's a square. It takes a square because error is equals to y minus y bar all squared, so that you take care of any negative numbers all squared. So there's a square here, so all of this squared. So now you see that the equation of error becomes equation of y, m, and b. So how does it get m and b? So if you plot a graph of error against m, keeping b constant. So if you keep b constant and then you plot a graph of error against m, so you have error on the y-axis and m on the x-axis, it's going to be like this. It's going to be a parabola. So you notice that the point where the error is least, so we're going to get a point where the error is least. The point where the error is least is this point. And so there is a corresponding value of m at that point where the error is least. So the value of m, whatever value of m it is here, let's say 4, is going to be the best, the value of m of that's going to be the gradient of the line when the error is least. Remember, the line of best fit is the line where the error is least. And if I do the same for b, keeping m constant, and I plot b against m, what is going to happen is that I'm going to have something like this against, sorry, e, not m, b against error. Then there's the point where the error is least is the point where there is a corresponding value for b, and again b is the y-intercept, is the point where the baseline cuts the y-axis. So let's say the point of b here is maybe say 10,000, right? Also, that's there. Now what we are saying in essence is that if I'm taking m against b, what I mean is that if b is constant, that means my y-intercept is going to be constant. That means I can have lines with different gradients, but all cutting at the same point. The same gradient cutting at the same points, right? These are different gradients, all cutting at the same point of the x-axis. And then when we are saying keeping b constant and then having changing b and keeping m constant is something like having a plot like this. Then you have the gradient is constant, but the gradient is constant, but they are cutting at different points on the y-axis, right? That's what we mean, keeping m and b constant. So it's going to do this and then get the corresponding value of, calculate the error for each of the lines. That is, each of the lines that gives the least error. It now gets the corresponding value of b and m for the corresponding error. And then that becomes the final, and then it fits that equation here. It fits those values here, and it will give it the equation of the line that has the least error, and that becomes the line of best fit. And so after that, once it has determined the line of best fit, now, when you come again to plot, when you bring now a new GPA, it now takes the line of best fit, say this is the line, it now takes that GPA, maps it up here, get the corresponding line, and then get the salary here, say 40,000. Is it clear? Is it clear? Is there any question? Okay. So, unsafe. There are different methods that the algorithm can use to get the line of best fit. The one I've explained to you is the one that is called OLX. So there are different methods. You have OLX, which means gradient, so there's gradient descent, there's regularization. OLX stands for ordinary least square method. So that's the one I've explained to you. So we are going to look at gradient descent and then regularization. These are the different methods that it calculates the line of best fit. So all the things I've explained to you are the things I've put here in this one note here. So the next thing we're going to do now is do an example where we do some plotting. We do examples of how to train a linear regression model. And then from there now, using the OLX method, and then from there, we continue. So this is going to be it for today. I'm actually still in the office and they're about to log the office and I need to rush. So in our next class, we're actually going to address, maybe we will just do the practicals and then we talk about gradient descent. And then, whichever we choose to, we'll start with gradient descent before we talk about regularization. And then we'll go to another model. Is that okay? Is it clear? Okay. No silence means all is good. See you all in the next class. Bye-bye.